Hi everyone, welcome to Lab 10. This is our lenses lab. And before we dig into any of the equipment, I'd like to dig into the theory a little bit, which is starting well with the lens equation. The lens equation looks like this. 1 over the distance to the object, dO, plus 1 over the distance to the image is equal to 1 divided by the focal length, f. Alright, what does any of that mean? Well, let me draw a diagram. Let's assume we have some kind of lens here. I'm going to draw a central line here. We've got an object that's just kind of hanging out there on this side of the lens, and we can say that the distance to the object is the distance from the lens to the object, dO. And the light from this object is going to go through this lens. Lens is going to bend, it's going to curve, and you're going to end up with an image of that object. On the other side, I'm going to put it upside down for now. So, the distance to the image is di. And there's some conventions that you probably should be aware of. In this case, both dO and di should be positive numbers. If di is ever negative, that means that you're ending up on the other side, or this side of the lens. In this case, the image is a real image. In this case, the image is a virtual image. We can dig more into that later. But for now, the last piece of this equation is the focal length. And the focal length is inherent to each lens. Every lens has its own different focal length. It has to do with the curvature of the glass that makes the lens, or whatever is making the lens. And it's just called f, the focal length of the lens. A way that you can think about it is if all the light was coming in parallel, all of that light would bend and intersect through to the focal point. If you've ever done this with a magnifying glass on a sunny day, you'll have seen this in action because you will have the sun producing, streams of parallel light going through a lens, and that light will all focus into the focal length of the lens, something like that, and create a very, very bright hot spot on the focal point here. And let me prove that to you by thinking about the lens equation. Think about the distance to the object. In this case, the object is the sun, which is basically infinitely far away. It's ridiculously far away to the point where we can just call it infinity. So in this case, we have 1 over dO, which is infinity, plus 1 over di is equal to 1 over f. Now 1 over infinity is just 0, so it's pretty quick to say that di is also equal to f. So the image distance of the sun is also the same as the focal length to the little hot spot of light. And there's one other equation that I wanted to show you before we got too deep, and that is the magnification equation, which we'll call big M. It's really just what it sounds like. It's how much bigger or smaller the image is compared to the object. One way that you can do that is just to look at the height of the original object and the height of the image that you're producing, and kind of do a ratio to figure out how much magnification there is. We're not going to look at any heights today, so let me show you another equation that will do the job here. Negative di divided by dO is also equal to the magnification. So you can figure out how much bigger or smaller the image is. Another convention piece here, if the magnification is ever negative, then that means that the image is upside down.